Hi, I'm David Nakazono. This summer I worked with Ryan DeCrescent in Alan Schuler's lab on increasing organic photovoltaic efficiency. So what is a photovoltaic cell? It's a solar cell, so that means it converts light into electricity. And basically there are two types. There's inorganic and organic solar cells. Inorganics tend to be silicon-based or some other semiconducting material, whereas organics are made from carbon-based materials. So here's a picture of the traditional kind of inorganic solar cell array, and just to familiarize yourself with what I'm working with. So why are we interested in organic photovoltaics? Well, as you can see in this picture, they're light, thin, and durable and flexible. So that avails them to many applications in devices, wearables, and many other technologies. So I know many of you have been playing Pokemon Go, and imagine you're working out, trying to catch them all, and your phone dies. Imagine if you just plug your phone into your shirt, your OPV shirt, and continue trying to be the best there ever was. So not only are OPVs offer many applications in different technologies, but they have a very efficient and cost and energy efficient production method, roll-to-roll printing. This makes them much cleaner than inorganic solar cells, which use harmful chemicals, a much more complex and expensive structure, and are much less environmentally friendly in manufacture. So there's all these cool applications and technologies available through organic photovoltaics, but unfortunately they lag behind in efficiency with inorganics. Inorganics hover around 35% efficiency in converting light to electricity, whereas organics are around 13%. So what the Schuler group wants to do is find a new approach that can enhance efficiency, and this approach we theorize to be taking advantage of optical anisotropies or directional dependencies in organic polymers and optimizing them so we can enhance efficiency. So what that looks like is some organic polymers have different orientations that are process dependent and can form these orientations depending on how you apply them to your sample, whether it be in different solutions or different concentrations of things. So here's one orientation, for example, an in-plane orientation where the organic polymer's strong absorbing axis is aligned parallel to the substrate. And what happens is when light enters the sample, it scatters. And right now it looks like the light is pretty well aligned with the strong absorbing axis. However, when converting light to electricity, we're interested in the electric field of light, which is perpendicular to this direction of travel. And now you can see there's very little correlation between the strong absorbing axis and the electric field. However, there's other orientations, for example, out-of-plane orientation, where now you can see the strong absorbing axis is much more strongly aligned with the electric field, which in the Schuler group we want to show would demonstrate enhanced efficiency. So before we begin characterizing these different orientations in organic polymers, we want to understand and characterize our substrate, which is composed of a quartz cover slip and gold film. The dielectric layer for now is air, but when we begin working with organics, it will be the organic polymer. So to characterize this gold film, we use a technique called momentum resolved spectroscopy, and what we do with that is we shine a laser at our sample, and Maxwell's equations tell us that when it changes media, it bends that light wave, and our momentum resolved spectroscopy technique allows us to change that incident angle very precisely. And at a point called the critical angle, all the light is reflected and travels along the gold film interface. And what that light wave in the gold is doing is the electric field is exciting little oscillations in the charges in the gold film. Now these charges by themselves, without light exciting oscillations, have a natural oscillation. So if we tweak this angle even more, we can reach a phenomenological point called the surface plasmon resonance, where the electric field matches with the natural oscillations and excites very large resonant oscillations. So surface plasmon resonance is just like any other resonance. So take, for example, an opera singer and a wine glass. That wine glass has a characteristic frequency that if the opera singer matches and sings into the glass, she can excite very large and violent vibrations such that it vibrates the glass to a point of shattering. So how do we know what's going on and figure out how the light interacts with the gold film? we can take reflectivity measurements and look at the reflected wave of light. Now, at the surface plasma resonance, the energy of the light wave goes into exciting these oscillations in the charges, so we get much less reflected light. We're looking at a model of what should happen in the gold film. We see that, so K parallel over K naught is just a representation that is a little more delineating in our experiments of angle of incidence. So it's parallel component of momentum over the total momentum, and just think of that as angle. At K parallel over K naught equals 1, the critical angle, we see a large uptick in reflectivity, and then soon after that we see the plasma resonance, the drop in reflectivity, which corresponds to a spike in absorption. So looking at our actual data, we can see the quartz cover slip by itself, no gold on top. The blue line starts off very little reflection as it just goes straight through the quartz. But once you reach the critical angle, it's all reflected. You get near 100% reflectivity. And looking at the red dots is our gold data. You can see that it matches the shape pretty well of the model. There's an uptick near the critical angle, and they drop at the plasma resonance. So we're interested in this gold film, and looking closer at our gold data, we see pretty good shape. And then what we need to do is look at very precisely where this plasma resonance is. So what we do is fit this data with a modified Gaussian to very pinpoint the minimum of where the plasma resonant would be, and then taking that plasma resonant location for different wavelengths allows us to generate a dispersion relation for this plasma. Now, what you can see here is a plot of wavelength versus the momentum. The light line here is just the momentum that light has when traveling through air. So at different wavelengths, it's got different momentum. And the red dots is our data, and the theory is our simulated values for each wavelength. You can see here that the data matches our theory very well, and this allows us to say that we've characterized our gold film. So now with our gold film characterized, we can move into organics, and what we want to do is use H1 histone, some organic polymer, which demonstrates this varying orientation. And we want to use in-plane and out-of-plane orientations to demonstrate the viability of optimizing orientations to enhance efficiency. So I'd like to acknowledge Sam Williamson, my lab partner, Ryan DeCrescent, and Stephen Brown are my mentors, John Schuler, the principal investigator, the Gorman Scholars Program, Dean Wiltius, and Office of the Dean, Math and Life and Physical Sciences. Any questions?
Why is characterizing the gold so important?
We need to know how light interacts with the substrate, and that absorption of where this plasma is very important for converting the light to electricity, because we need the light to be absorbed into the sample.
So you started the talk with applications for OPV materials that are already being created, like thin film cells. What is the technology that they're using if it's not gold?
Well, we're using gold as it's a good conductor and demonstrates these plasma characteristics in the visual and ultraviolet, or visual and infrared frequencies. And basically, the construction of organic solar cells is you have a couple electrodes, so metal layers, and then the organic polymer. So we're looking at a simplified kind of idealized version.
So they're using like a cheaper, more affordable metal? Is that?
Not necessarily, I don't think. I'm not totally sure what they're using, but I know gold and silver are pretty traditional metals to use for these experiments.
So are you using gold for the plasmon resonance to like upconvert photons, or investigating that at all?
I'm not sure what the question is.
Sorry. So surface plasmons, they have that resonance, they can amplify things. Are you trying to upconvert incident photons at all with that?
Well, what we're doing is trying to characterize this gold film so we know where the maximum absorption occurs for each wavelength, and that's mostly it. So we can get better absorption when looking at organic polymers.
During plasmon resonance, what's like the order of magnitude for the oscillations?
I'm not sure about that.
What's the lifetime of the OPVs that you're working with?
I believe they're fairly stable, but I know some organic polymers do decay with light. I don't know exactly how lifetime is though.
So once you're done characterizing the gold, what is the next step in the process?
Creating new samples with the organic polymers and then characterizing, doing the same measurements with the organic polymer out there.
So which organic polymer did you use for summer?
We didn't use any organic polymers for the summer. We just characterized the gold film. We will be using H1 histone in the upcoming weeks.
Is the H1 histone, did you select that because there's been some prior research done on that?
Well, there's a lab on campus that can make it for us, and it demonstrates the different orientations that we're interested in. So it's just a good material to use.